Okay, here is question number 1. It says engineers must consider the diameters of heads when designing helmets. The company researcher has determined that the population of potential clientele have head diameters that are normally distributed with a mean of 6.6, standard deviation of 0.9. Due to financial constraints, the helmets will be designed to fit all men except those with head diameters that are in the smallest 3.8 or largest 3.8%. So they follow the normal distribution with a mean of 6.6. So mu is 6.6. And my sigma is 0.9. So it wants us to find the minimum head length, the head width that cuts off the bottom 3.8% and the top 3.8%. So if I draw my normal curve, let's see if I can, it's always hard to draw on this thing, the normal curve. Actually, let's do it this way. So I'll draw my line first, and then the curve like this. Ooh, okay, that's good enough. The mean is 6.6. So I'm looking for the value that cuts off the bottom 0.038 and the top 0.038. So I'm looking for this x value. We'll call this x1, and we'll call this x2. Okay, so we're going to use the calculator to figure this out. So we're going to go to the distributions menu, and we're going to use the normal CDF, because we're talking about the normal curve. Okay, so no, that's not what we would do inverse normal because we're looking for the values. Second, distributions. When we have the percentage, we want to use inverse normal. My mistake. Clear out of that. Quit out of that, and we'll do second inverse normal. So it wants to know the area. So whenever the calculator asks for the area, it's always asking for the area to the left of something. So I'm going to find x1 first. So the area to the left of this x1 is going to be 3.8% or 0.03. So I'll do 0.038. My mu is 6.6. My standard deviation is 0.9. Hit paste. So this means the smallest head they'll fit is 5.00. One decimal place, so we'll just say 5.0. Now I'm going to do the same thing, but with x2. So how much area is to the left of x2? Well, if there's 0.038 above x2, then to find the area below it, I'm just going to do 1 minus 0.038. So that means there's 96.2% from here over. So this is going to be 0.962. So I'll just do the same thing. Inverse normal. 0.962. Everything else stays the same. And I get 8.19 or 8.2. That's it. Okay. Okay. Second one, this is a long one, but it's not that crazy. It says the population of weights for men attending a local health club is normally distributed with a mean of 169. Mean is 169. Standard deviation is 30. An elevator in a health club is limited to 32 occupants, but will be overloaded if the total weight is in excess of 5,984 pounds. Assume that there are 32 men in the elevator. It's a big elevator. What is the average weight beyond which the elevator would be considered overloaded? How much can each man weigh on average? Well, this is the most they're allowed to weigh, and there's 32 of them. That means each man can weigh 5,984 divided by 32. Each man can weigh 187 pounds. If they all weigh more than that, that's a problem. If they all weigh less than that, it's fine. But they have to be on average 187, or otherwise the elevator will be overloaded. So this says, what is the probability that one randomly selected male health club member will exceed this weight? So the probability that one male will be more than 187. So they're normally distributed, remember. I'm going to draw my curve over here with a, let's see if I can do this curve again. With a mean of 169. I want to know what's the probability, here's 187, of them being larger than that. So I'm looking for that area. So now I'm going to use the normal CDF because I'm looking for the probability. So the lower bound is going to be 187. The upper bound, there is no upper bound. This goes on forever. This goes on forever in this direction. So we just pick a really, really, really large number. I'll do like 100,000, whatever. Just pick a bunch of zeros. My mu is 169. Sigma is 30. So the chance that one specific man exceeds that weight is 27.4%. It wants it for so 0.2743 to 4 decimal places. So the next question says, if we assume that 32 males are a result of a random selection, right? We're talking about a sample now. This is a sample. Find the probability the elevator will be overloaded. So now we're trying to figure out what's the chance that the average of these 32 is greater than 187 from a sample. When we're talking about a sample, the only thing that changes is our sigma. The sigma from our sample is going to be equal to the sigma of the population divided by the square root of n. So our sigma is going to be, you can just write it in the calculator just like that. So we're still going to do the exact same thing. Nothing's going to change except for sigma. Normal CDF. Now my sigma is 30 divided by the square root of the sample size, 32. 32 men. So it's 0.0003. So basically we'll do 0.0003. Oops. Okay. So now it says if the elevator is full on average 2 times a day, how many times will the elevator be overloaded in one non-leap year? So this is how often, or the probability that it gets overloaded with 32 people. So I'm just going to take that number, 0.0003. It's overloaded 2 times a day, or it's full 2 times a day. So that's 365 days a year. So we get 0.219. So basically, this is saying that if this is all true, that it'll be overloaded 0.219 times, or basically it'll be overloaded 0 times, less than 1 time. Okay, kind of a weird way to look at it, but if this number was like it could be like 5.67. That would mean it was overloaded 5 times. But since it's less than 1, we'll just say it's overloaded 0 times. So since it's overloaded 0 times, then we could say that the current overload limit is adequate to ensure the safety. If it's never ever going to be overloaded in a year, we can ensure that that's safe enough for people to ride the elevator. Okay. Now this one here, the town of Nowhere Spatial. That's funny. USA operates a rubbish waste disposal facility that's overloaded if its 4,600 households discard waste with weights having a mean that exceed 27.37. For many different weeks, it is found that the samples of 4,600 households have weights that are normally distributed with a mean of 26.92, standard deviation of 12.62. What is the proportion of weeks in which the waste disposal facility is overloaded? So it's overloaded when the mean exceeds that. Okay, so let's draw out our we're talking about a mean now. Okay, the average. If the average of these households exceeds, so let's see, it's 26.92, sorry, and sigma is 12.62. I'm looking for the probability, or what percentage is above 27.37. Okay, so I'm looking for this area. What probability will be of weeks will it be overloaded? Basically, what percentage of samples will be overweight? So when we're looking at a sample, we have to make sure we use the sigma for a sample. So our sigma with respect to the sample is going to be the sigma 12.62 divided by the square root of the sample size. Okay, so we'll just plug it in the calculator the way it's written. So we have second distribution, normal CDF. Lower bound is going to be 27.37. Our sigma is going to be 12.62 divided by the square root of 4,600. Paste, enter. We get 0.00779. 4 decimal places will be 0.0078. Now it says, is this acceptable or should action be taken to correct the problem of an overloaded system? It only occurs 0.78% of the time. So it doesn't occur very often. Okay, so I'd say this is an acceptable level because it's unusual for the system to be overloaded. Usually we say if it's above or below 5%. This is below 1%. So it's very unusual that this happens. So it's an acceptable level. So we say the answer is yes. And the last one, the time required to assemble a single PlayStation 3 is approximately normal. Mu is 16.06 and sigma is 1.8. A random sample of 15 PlayStation 3 assembly times is selected. Find the minimum assembly time of the upper 10%. Let's do it again. Here's our curve. The average assembly time is 16.06. Sigma is 1.8. But we're talking about a sample. So we want to know the probability of the sample having an average of that. So we're looking for this, the top 10%, which means we're cutting off the bottom 90%. When you're given the percentages, you're going to use inverse normal. Second distribution, inverse normal. Oops, that's all I want. Second distribution, inverse normal. Get out of here, get out of here. Inverse T, I don't want that. Second distribution, inverse normal. There we go. The area to the left of this value that I'm looking for is 90%. My mu is 16.06, but since I'm talking about a sample, I have to change my sigma. It's going to be 1.8 divided by the square root of 15, the sample size. So we get 16.655 or 16.656. I think you're just forgetting, if you see this word sample, always make sure your sigma of your sample is equal to sigma of the population over the square root of n. That's the most important thing to remember.